Isn't it wild to think that almost everything we see isn't shining on its own?
Yeah, it's just borrowing light.
Exactly. Bouncing it back to our eyes.
Yeah.
That return trip, well, that's reflection.
Mm-hmm.
And that's exactly what we're plunging into today,
Mm-hmm.
the reflection of light. We're really going to zero in on those polished surfaces, mirrors.
Right. Both the flat ones and the curvy kind.
Yeah.
Precisely. And you've given us a fantastic set of materials here. They really dig into how light reflects, the sort of rules it follows.
The laws of reflection, yeah.
Exactly. And how different mirrors shape the images we end up seeing.
So our mission, basically.
Well, I think we want to pull out the core ideas, right? The surprising bits, maybe some practical uses, but then understand why this seemingly simple thing is, well, so fundamental.
Okay. And we want to keep it clear, engaging, not get totally bogged down in the jargon.
Absolutely. Get right to the heart of it.
Okay, let's start with something super familiar. A regular flat mirror. A plane mirror. Your sources explain that reflection happens when light hits a surface and heads back
Yeah.
into the same space it came from.
Right. Back into the same medium.
And we see things that glow, luminous objects, because they make their own light. But like this table, my hand,
Non-luminous. They're just reflecting light from somewhere else.
in a really smooth surface, like that plane mirror, it's like a champion reflector, isn't it? Sends back almost all the light.
It does. And what's fascinating about a plain old mirror, as you called it, is that there's a bit more engineering there than you might first think.
Oh, yeah.
Sure, there's the glass plate, but the real reflection, the part that makes it work so well, that happens behind the glass.
Buying it.
Yeah. There's usually a super polished surface first, but then a thin layer of metal, often silver, coated on the back of the glass.
Oh, okay.
And then that's protected by paint, usually some opaque coating. That layering is really key for a sharp image.
That makes sense. Now, the material mentions two kinds of reflection, regular and irregular.
That's right. Regular reflection is what you get with those very smooth surfaces, like our mirror. Parallel light rays come in.
And they stay parallel coming out.
Exactly. Which means you kind of have to be in the right spot to catch that reflection, like seeing a glint.
Okay. And irregular or diffused.
That's for rougher surfaces.
Yeah.
Think about a piece of paper or wood or cloth, even if they feel smooth to us.
Microscopically, they're bumpy.
Precisely. And those tiny bumps scatter the incoming light rays. They bounce off in all sorts of directions.
So each little ray still follows the rule.
Oh, absolutely. The basic laws still apply to each individual bounce.
But the overall effect is just light everywhere.
Yeah, it gets diffused.
Yeah.
And that's why you can see this non-glowing book, say, from almost any angle in the room.
Right. It's the scattered light reaching our eyes.
It's fundamental to how we see most of the world around us.
Okay, this seems like a good time for some key terms your sources bring up.
Definitely helps to have the language straight.
Right. So the light heading towards the mirror, that's the incident ray. The spot where it hits is the point of incidence.
Got it.
And the light bouncing off is the reflected ray.
Okay.
Now, this next one's important. Imagine a line sticking straight out from the mirror, perpendicular, right at that point of incidence.
Okay, like a T-square against the surface.
Yeah, that's the normal.
The normal, right.
And the angle between the incoming ray and that normal line, that's the angle of incidence. We call it I.
Angle I, okay.
And the angle between the outgoing ray and the normal, angle of reflection, R.
Angle R, makes sense.
And all this happens like on a flat plane, right? The incident ray, the normal, the reflected ray.
They all lie in the same plane. That's actually part of the laws.
Ah, okay. So what are the laws then? There are two.
Two very elegant laws, yes. First one, and it's beautifully simple. The angle of incidence always equals the angle of reflection.
Oh, yeah, always.
Always. For any reflection. And the second law is what you just touched on. The incident ray, the reflected ray, and the normal at the point of incidence. They all lie in the same plane.
Keeps things neat and predictable.
It does. No weird sideways bounces.
Your sources also mentioned a special case. What if the light hits dead on, perpendicular to the mirror?
Ah, yes. Normal incidence.
So the incident ray is the normal, basically. The angle I is 0.
Right. And if I is 0, then the first law tells us.
R must also be 0.
Exactly. So the reflected ray just goes straight back along the path it came. Like a U-turn, as you said.
Huh. Neat. And people actually test these laws.
Oh yeah, the material mentions a classic experiment. You can do it with just pins, a drawing board, and a mirror strip.
Really? How?
Well, you stick pins in to mark the path of an incident ray. Then you look in the mirror and place other pins so they line up perfectly with the reflections of the first pin.
Ah, marking the reflected ray's path.
Exactly. Then you draw the lines, measure the angles with the normal, and you see that I equals R, and they're all in the plane of the paper. It's a very direct way to see it works.
Cool. Okay, so we know light bounces according to these rules. How does that create the images we see?
Right. Well, to figure out where an image appears, you need to trace at least 2 rays coming from a single point on the object.
2 rays minimum.
Yep. See where they go after reflecting. And this leads us to a really important distinction. Real versus virtual images.
Okay, what's the difference?
A real image is formed where the reflected light rays actually physically converge or cross.
They really meet up.
They really meet up at a point in space. Because they meet, you could put a screen there, like a piece of paper, and you'd see the image projected onto it.
Okay.
Real images are also typically inverted, meaning upside down relative to the object. Think about maybe using a magnifying glass to focus sunlight onto paper, that bright spot. That's a real image of the sun.
I see. So what's a virtual image then? Sounds less real.
It kind of is. A virtual image forms where the reflected rays don't actually meet. Instead, they diverge. They spread out after reflecting. But our brain extends those diverging rays backwards behind the mirror to a point where they appear to originate.
So our brain is kind of constructing the image.
In a way, yes. It assumes light travels in straight lines. So you can't project a virtual image onto a screen because the light isn't actually there.
And they're usually upright.
Typically, yes, erect or upright. And the classic example is the image you see of yourself in a regular flat bathroom mirror.
That's virtual. My reflection isn't really behind the glass.
Nope. It just looks like it is because of how the light rays reach your eyes. Your brain's being cleverly fooled.
Huh. Okay. Your material had some diagrams showing this for plane mirrors.
Yeah. They show tracing rays from, say, the top of an object and the bottom.
And for a plane mirror, the key takeaway is that the image is always virtual.
Always virtual. The rays always diverge after bouncing off the flat surface, so you always have to trace them back.
And there's something about the distance, too.
Ah, yes. A really useful characteristic. The image formed by a plane mirror appears to be located exactly as far behind the mirror surface
as the object is in front of it.
Precisely. Measuring perpendicularly, straight across, it's a perfect symmetry.
And that's not just coincidence.
No. The sources show you can actually prove it using basic geometry. Similar triangles. Congruent triangles based on the laws of reflection. It falls right out of the math.
Okay. Then there's that weird left-right flip, lateral inversion.
Mm-hmm. You raise your left hand.
The reflection raises its right hand.
Exactly. The source used the example of a ring on your left finger appearing on the image's right finger.
But it's crucial. It's not an up-down flip, right? Just side to side.
That's a common misconception. It's only lateral inversion. Your head is still up, feet are still down in the reflection.
Are there things that don't get flipped?
Well, letters that are symmetrical horizontally, like A, H, I, M, O, T, U, V, W, X, Y, they look pretty much the same in a mirror.
Oh, yeah. Huh. But this lateral inversion, it has practical use.
A very important one. Think about the word ambulance.
It's written backwards on the front of the vehicle.
Right. Why? So that when drivers ahead look in their rearview mirror,
the mirror's lateral inversion flips it back the correct way so they can read it instantly.
Exactly. Helps them recognize it's an emergency vehicle needing to pass. Clever application.
Very clever. Okay, so let's sum up the image in a plane mirror. It's upright.
Upright or erect.
Virtual.
Virtual, can't be projected.
Same size as the object.
Yes, magnification is one.
And laterally inverted.
Laterally inverted. Those are the key characteristics.
Oh, and here's a fun one from the source. The speed thing.
Yeah.
If you walk towards a plane mirror.
Yes. Say you walk towards it at 1 meter per second.
Your image appears to be coming towards you.
At 2 meters per second, because the distance between you and your image is shrinking at twice your speed. You're moving, and your image is moving behind the mirror.
Whoa. Okay. That's kind of mind-bending.
It is a bit, yeah. The relative speed is doubled.
The material also briefly mentioned thick mirrors, seeing multiple images.
Right. If the glass is thick, you can get a faint reflection from the front surface of the glass, as well as the main bright reflection from the silvered back surface. Sometimes even fainter ones from multiple bounces inside the glass.
But the main one, the brightest, is from the back coating.
Usually, yes. The second image formed by reflection at the silvered surface is the brightest.
Okay. And comparing a mirror to a wall helps understand regular versus irregular reflection.
Yeah, shine a narrow beam of light. On the mirror, you see a distinct spot reflected, regular. On the wall, the light scatters, illuminating a wider area, diffuse or irregular.
Gotcha. Okay, so that's single plane mirrors. But what if you put two of them together at an angle?
Ah, now things get really interesting. Multiple reflections.
More than one image.
Oh, yes. The image formed by the first mirror acts like a virtual object for the second mirror.
And then the image from the second acts as an object for the first.
Exactly. The light bounces back and forth, creating a whole series of images.
Wow. And the sources mentioned something about a circle.
Yeah, that's a neat geometric property.
Yeah.
The original object and all these multiple images, they all lie on the circumference of a circle.
And the center of the circle is?
The point where the edges of the two mirrors meet. Or where they would meet if extended.
Cool. And can we predict how many images we'll see?
Yes, there's a formula for that based on the angle between the mirrors. Let's call the angle theta.
Okay, theta.
First, you calculate a number, let's call it n, by dividing 360 degrees by theta. So n equals 360 degrees.
Okay, n equals 360 divided by the angle.
Now, there's a slight twist. If this number n turns out to be an odd integer, like 5 or 7, then the number of images you actually see depends on where the object is placed. If it's asymmetrical off to one side, you see n images.
So 5 images if n and 5.
Right. But if the object is placed symmetrically exactly on the angle bisector between the mirrors,
Right in the middle.
then 2 of those images overlap and you only see n1 images.
So 4 images if n5 and it's symmetrical. Huh. Now what if n comes out as an even integer, like 4 or 6?
What happens then?
It's simpler. You always see n1 images regardless of where the object is placed between the mirrors.
Always one less than the calculated even number.
Exactly. The material gave examples, like if theta is 72 degrees, n equals 36072, well 5 odd. So you see 5 or 4 images. Okay.
If theta is 60 degrees, n equals 36060 equals 6 even. So you always see n1 equals 5 images.
That's pretty specific. Does it always work?
It's a good rule of thumb, especially for simple cases. Realistically, the later images get very faint.
Right. Speaking of which, the sources mention special cases. Parallel mirrors, like in a zero.
Ah, yeah. If the mirrors are parallel, facing each other, theta is 0. The formula 3600 gives, well, infinity.
Infinite images.
Theoretically, yes. The light bounces back and forth forever. But as you said, each reflection absorbs a little light.
So they get dimmer and dimmer.
Rapidly dimmer. You only really see a few, clearly. But you see this effect used.
Oh, yeah. Barbershops or hair salons so you can see the back of your head.
Exactly. Or sometimes in fitting rooms or showrooms to make the space feel larger.
And the other special case, perpendicular mirrors, 90 degrees.
Right, so n in little 36090 equals 4, which is even.
So we see n1 equals 3 images.
Correct. 3 images. The ray diagrams show how one mirror's image acts as a virtual object for the other, and one pair of virtual images ends up overlapping perfectly.
And they still lie in that circle.
Yep, the object and the 3 images are still on a circle centered at the corner where the mirrors meet.
Plane mirrors seem way more versatile than I thought. Looking glasses, obviously.
The most common use.
But opticians' rooms, to make them seem longer.
Yeah, using mirrors to increase the effective distance for eye charts in small rooms.
Barbershops we mentioned. Periscopes.
Classic use. 2 plane mirrors tilted at 45 degrees inside a tube let you see over obstacles.
And kaleidoscopes, those use 60-degree angles, right?
Typically 3 mirrors forming an equilateral triangle, so 60 degrees between them, creating those beautiful symmetrical patterns from multiple reflections.
Even solar heating sometimes.
Yeah, large, flat mirrors called heliostats can be used to track the sun and reflect its rays onto a central collector.
Okay, wow. That's a lot for flat mirrors. Let's curve things up. Spherical mirrors.
Right. Moving beyond flat surfaces, as the name suggests, these are sections of a sphere.
Like you take a hollow glass ball and slice a piece off.
Essentially, yes. And then you make one of the surfaces reflective, usually by coating it.
And there are 2 main types based on which side reflects.
Exactly. Concave and convex.
Concave, like a cave. It curves inwards.
That's the one.
Yeah.
The inner scooped-out surface is the reflecting side. The outer surface is coated.
And it does what to light?
It converges parallel light rays, brings them together, so it's a converging mirror.
Okay, and convex.
Convex bulges outwards. The outer surface is the reflector, and the inner surface is coated.
And it must do the opposite.
It does. It diverges parallel light rays, spreads them out. It's a diverging mirror.
Got it. Converging cave, divergent bulge. Now more terms.
A few key ones for spherical mirrors, yeah. Think back to that original sphere the mirror was cut from.
Okay.
Its center is called the center of curvature, symbol C.
Center of the whole sphere, right.
The distance from that center C to the mirror's surface is the radius of curvature, R.
Okay, radius R.
The geometric center of the mirror's actual reflecting surface is called the pole, P.
P for pole.
The width or diameter of the reflecting surface is the aperture.
Aperture, okay.
And a really important one, the principal axis. It's an imaginary straight line that passes through both the center of curvature, C, and the pole.
The main line through the middle. Got it.
And crucially, reflection from these curved surfaces still follows the exact same two laws we talked about earlier.
Angle I equals angle R, and they stay in the same plane.
Absolutely. The only trick is figuring out the normal at any point on the curve.
How do you do that?
Remember, the normal is always perpendicular to the surface. For a sphere, any line drawn from the center of curvature C to the surface is automatically perpendicular to the surface at that point.
So the normal is just the line connecting C to the point of incidence.
Exactly. That makes drawing ray diagrams manageable.
Okay. Now, spherical mirrors have this thing called a focus, F.
Yes, a very important point. And the distance from the pole P to the focused F is the focal length, F.
And it's different for concave and convex.
It is. For a concave mirror, if parallel rays come in, parallel to the principal axis, after reflecting, they all converge and pass through a single point on the principal axis. That point is the principal focus, F.
So they actually meet there. Is it a real focus?
Yes, it's a real focus because the rays physically converge there.
And for convex, they diverge light.
They do. So parallel incoming rays reflect and spread out. They don't meet in front of the mirror.
Right.
But if you trace those diverging reflected rays backwards, behind the mirror, they appear to originate from a single point on the principal axis. That's the virtual focus for a convex mirror.
Virtual focus. Okay.
Right.
Real focus for concave, virtual for convex.
Correct. And related to that is the focal plane, an imaginary plane passing through the focus, perpendicular to the principal axis. Parallel rays coming in at a slight angle will focus somewhere on this plane, or not necessarily right at F.
Okay. Now, drawing these diagrams to find images. It sounds tricky.
It can be, but luckily there are a few convenient rays whose paths are easy to predict. Usually drawing just two of these is enough to locate the image.
Oh, good. What are they?
Okay, four main ones. First, a ray traveling through the center of curvature, C, towards the mirror.
That hits perpendicular, right, because it's a radius.
Exactly. So it hits with I0 and reflects straight back along the same path. Through C again?
Easy enough. Ray 1 through C, back through C.
Ray 2. A ray coming in parallel to the principal axis.
We just talked about those.
Right. After reflection, it will pass through the focus, F, if it's a concave mirror.
Or appear to come from the focus, F, if it's a convex mirror.
Perfect.
Right.
Ray 3 is basically the reverse of ray 2, a ray that passes through the focus, F, on its way to a concave mirror.
Will reflect parallel to the principal axis.
Yep. Or for a convex mirror, a ray that is aimed towards the virtual focus, F, behind the mirror will also reflect parallel to the principal axis.
Okay. Rays from F become parallel. Makes sense. Last one.
Ray 4, a ray that strikes the pole of the mirror.
Right at the center.
Here, the principal axis itself acts as the normal, so the ray reflects off, making the same angle below the axis as it made above it coming in. Angle I equal I angle R, relative to the principal axis.
Okay, pole bounce follows the simple law, so pick two of those four.
Usually, yeah. Draw them from a point on the object, like the top, see where the reflected rays intersect or appear to intersect, and that's where the image of that point will be.
Okay, now your material went through all the possibilities for a concave mirror, depending on where the object is.
It's important because the image changes dramatically.
Right. Object at infinity, like stars.
Image forms right at the focus, F. It's real, tiny, a point, and inverted.
Bring the object closer, but still way beyond C.
Image forms between F and C. Still real, still inverted, but now it's smaller than the object, diminished.
Object right at C.
Image forms right at C2. Real, inverted, and exactly the same size as the object. A special point.
Okay, now move the object between C and F.
Now the image forms beyond C. It's still real and inverted, but now it's magnified larger than the object.
Getting bigger. What if the object is right at the focus, F?
The reflected rays become parallel. They never meet. So the image is theoretically formed at infinity. Real, inverted, and infinitely magnified.
Whoa. Infinity.
It's the principle used in searchlights or headlights. Put the bulb at F to get a parallel beam.
Ah. Okay, one more case for concave. Object between F and the mirror. P, really close.
This is the game changer. Now, the reflected rays diverge. They don't meet in front.
So, virtual image.
Exactly. You have to trace them back behind the mirror. And the image you see is virtual, it's upright, and it's magnified.
That's the shaving mirror effect.
Precisely. Or a makeup mirror. You put your face close to see a larger upright version.
So concave mirrors can do pretty much everything depending on where the object is. Real, virtual, bigger, smaller, inverted, upright.
They're very versatile. The provided table summarizing this is really helpful.
Definitely. Now, what about convex mirrors? The outward bulging ones.
Much simpler. The sources show, and the ray diagrams confirm, that no matter where you place a real object in front of a convex mirror,
The image is always
virtual, always upright, and always diminished, smaller than the object.
always. That's easy to remember.
And it's always located behind the mirror, somewhere between the pole, P, and the virtual focus, F.
So the table for convex mirrors is much shorter.
Much shorter. As the object gets closer to the mirror, the virtual image also gets closer and slightly larger, but it never becomes real or magnified or inverted.
Okay, now there's a link between the focus and that center of curvature.
A very direct one. For spherical mirrors, at least ones where the aperture isn't too huge, the focal length, F, is exactly half the radius of curvature, R.
F is R2, always.
For spherical mirrors, yes, the sources might show a geometric proof, but the relationship F equals R2 is the key takeaway.
Good to know. Okay, before we hit formulas, we need signs. Positive and negative.
Yes, the sign convention. Crucial for using the formulas correctly. The standard is the Cartesian sign convention.
Like coordinates in math.
Kinda, yeah. The pole, P, is the origin, 0, 0. The principal axis is the x-axis.
Okay. Light comes from...
Conventionally, incident light comes from the left towards the right.
Okay. So distances measured left to right are...
Positive. Distances measured right to left against the incoming light are negative.
So object distance U is usually measured from P to the object on the left. So U is usually negative.
Often, yes, if the object is real and to the left.
And image distance V.
Measured from P to the image. If the image is real, formed on the left by converging rays, U might also be negative. If it's virtual, formed by the mirror on the right, B would be positive.
What about heights? Above and below the axis.
Heights measured upwards from the principal axis are positive. Heights measured downwards are negative.
Okay. And focal length F.
This is important. For a concave mirror, the focus F is typically on the left, real focus, so its focal length F is taken as negative.
Concave F is negative.
For a convex mirror, the focus F is behind the mirror, virtual focus on the right, so its focal length F is taken as positive.
Convex F is positive. Got it. That seems really important to track.
Absolutely critical for the formulas.
Speaking of which, the mirror formula.
The big one. 1F equals 1U plus 1V.
1 over focal length equals 1 over object distance plus 1 over image distance.
That's it. Works for both concave and convex mirrors, as long as you use the sign convention correctly.
And magnification, how much bigger or smaller the image is.
Magnification M is the ratio of image height pi to object height O, so M equals I-O.
Okay, image height over object height.
And it also equals negative image distance over object distance.
MFU.
I want a new sign.
That minus sign is handy. It ties into the sign convention. If M calculates out to be negative, it means the image is inverted and real, usually. If M is positive.
Upright and virtual.
Exactly. The sign of M tells you the orientation. The number tells you the size change. M2 means twice as big. M 0.5 means half the size. Okay, that's super useful. Right, let's connect this to uses. Concave mirrors. We said shaving makeup mirrors.
Yep. Object between P and F for magnified, virtual, upright image.
And reflectors in torches, headlights.
Bulb placed at the focus F to produce a parallel beam of light. Maximizes the throw distance.
Dentist's mirror.
Often concave, used either to magnify a tooth, like a shaving mirror, or sometimes a head mirror used to focus light from a lamp into the patient's mouth. Medical examiners might use them too to focus light or get magnification.
Okay. And uses for convex mirrors, the diverging ones.
Main one is rear view mirrors in vehicles, side mirrors especially.
Why them?
Because they diverge light, they give a much wider field of view than a flat mirror of the same size. You can see more of the road behind you.
Even though the image is smaller.
Yes, the trade-off is a smaller image, but it's always upright and virtual, and the wide view is crucial for safety. The source might have a diagram showing that wider view.
Yeah, comparing it to a plane mirror makes sense. Also, street lamps?
Sometimes used as reflectors above the bulb in street lamps to spread the light downwards and outwards over a wider area.
Okay, now, the source had a cool trick. How to tell plane, concave, and convex apart without touching them.
Yeah, just by looking at your reflection.
So hold it close to your face and move it away.
Exactly. What does a plane mirror do?
Image stays the same size, upright, virtual.
Right. What about concave? Start close.
Closer than F, magnified, upright, virtual image.
Okay, now move it further away. Past F, past C.
The image gets smaller and flips. Becomes inverted and real, though you can't see real easily without projecting.
Right. That changed magnification then inversion signals concave and convex.
Always upright, always virtual, always smaller. And as you move it away, the image gets even smaller.
Perfect. That distinct behavior lets you identify them.
And the material wrapped up with a nice table comparing concave and convex directly.
Yeah, summarizing the reflecting surface shape, action on parallel light, focus type, and typical image nature. Very handy.
Plus some worked examples applying the 1F = 1U plus 1V and M equals of VU formulas.
Good for seeing the sign convention in action.
Definitely. Okay, so let's try and quickly recap this deep dive then.
Sounds good.
Reflection, whether it's off a flat plane mirror or a curved spherical one, it all boils down to those same two basic laws, right?
Angle of incidence equals angle of reflection, and they all lie in the same plane. That's the bedrock.
Plane mirrors give us those predictable images. Virtual, same size, upright, but flipped sideways.
Lateral inversion, yep. Useful for ambulances and seeing yourself.
Spherical mirrors, though, they offer more variety. Concave can converge light, make real images, magnify, or act like a makeup mirror.
Depending entirely on where the object sits relative to C and F.
While convex mirrors always diverge light, always give a smaller, upright virtual image with a wide view.
Great for seeing what's behind you on the road. And it all ties together with FR2, the mirror formula, and the magnification formula if you just keep track of those signs.
Absolutely. You know, what's really remarkable, thinking about it, is how these pretty simple principles of reflection, they're not just in our bathroom mirrors.
Oh, far from it.
Yeah.
They're absolutely fundamental to so much advanced technology.
Life.
Well, think about giant astronomical telescopes gathering faint light from distant stars and galaxies. That's all about precisely shaped mirrors reflecting light to a focus.
Huge concave mirrors, basically.
Often, yes, or combinations of mirrors. Or think about fiber optic cables carrying internet data across the globe.
Uses reflection, too.
Totally. It relies on total internal reflection, light bouncing continuously inside a thin glass fiber, carrying information over vast distances with very little loss.
Wow. So from a simple mirror to global communication.
It really shows how understanding something fundamental about light, like reflection, opens the door to incredible innovation.
So maybe a final thought for you listening, now that we've unpacked reflection a bit.
Maybe start noticing it more. When you see a reflection in a shop window, a puddle, a shiny car, think about whether it's regular or diffuse, maybe even what kind of curve might be involved.
You see the physics in action all around you.
Exactly. It adds another layer to how you see the world.